We're going to talk about identities. That would be trigonometric identities. You're going to notice here that the title is Identities Part 1. We'll actually be doing this in two parts because there are a lot of trigonometric identities that we need to get through. One of the things that you're going to notice as I go through the identities is that I'm going to make my best effort to try and get everything in terms of either sine or cosine. Okay, so we've got 6 trig functions, we've got sine, cosine, we've got tangent, we've got the reciprocals of those, cosecant, secant, and cotangent. But my goal is going to be, most of the time here, is going to be trying to get everything in terms of sine and cosine. That way I'm only looking at 2 functions versus looking at 6 of them. All right, what we have first here are the identities by definition. All right, so cosecant is the reciprocal of sine. So the cosecant of theta is equal to 1 divided by the sine of theta, okay? The secant of theta is the reciprocal of cosine. So we could write that one as 1 divided by the cosine of theta. All right, now those two are technically referred to as the reciprocal identities. All right, now for the other two here, tangent and cotangent, they are reciprocals of each other, right? So what I don't want to do here is write down that the tangent is the same thing as 1 divided by cotangent theta. And I don't want to write down that cotangent theta is equal to 1 divided by tangent theta. My goal is always going to be to try and get things in terms of sine and cosine. So here's what the sine of theta is actually equal to. It's equal to the sine of theta divided by the cosine of theta. Those two things are actually equal. All right, so let's go ahead and take a moment to verify that this is actually true. Okay, so my claim here is that the sine of theta divided by the cosine of theta is equal to the tangent of theta. Okay, so I'm going to think of this backwards because it's going to be a little bit easier to demonstrate here. All right, going back to the definitions, the sine of theta is equal to the y value divided by the radius. The cosine of theta would be equal to the x value divided by the radius. All right, so I'm going to focus on just this part here. What I have are 2 fractions that are being divided, and if we're dividing fractions, we can use a technique called keep, change, flip. That means that you keep the top fraction as it is, you change the division into multiplication, and then make sure you multiply by the reciprocal here. So that would be r over x. So when we do that, the r values actually just cancel out with each other. They cancel out, and we're left with y over x, which is the definition of tangent theta. All right, so the tangent of theta is equal to sine of theta divided by cosine theta. And if the cotangent of theta is the reciprocal of tangent, we can actually write that as cosine theta divided by sine theta. All right, next what we're going to do is look at the negatives, also referred to as the even and odd identities. And what we want to do here is make a comparison between a trig function with an angle and that trig function with the opposite of that angle, the negative of that theta that would go in there. So let's start with the sine of theta and the sine of negative theta, and then we'll take a look after that with the cosine of theta and cosine of negative theta. All right, using the unit circle, which we've applied many times here, what we can do is get a concept of how these two would really compare. Now remember that theta, if we do treat that as a positive angle, that rotates up. It rotates up from the positive x-axis that we have here. Negative theta is going to rotate in a down direction. Okay, so we are thinking that the thetas are the same size. It's just this rotates up and that one is going to rotate down. Okay, so we see that in the picture here. Now, of course, here our theta only goes into quadrant 1. The same arguments for everything that we look at here, the same arguments would hold true if we rotated all the way to like quadrant 2. Okay, negative theta would just rotate all the way to quadrant 3. All right, so we'll go ahead and just take a look at it, those being quadrant 1 and 4. All right, so for sine, when we rotate upward into quadrant 1, we get positive answers. Same thing if we go to quadrant 2. But when we rotate down into quadrant 4 or down into quadrant 3, those will give us negative answers. Okay, so there's definitely going to be a difference between the type of value that we'll get here with the positive versus negative. However, they do have the same reference angle, right? Whatever that angle is here, that's the same measurement there. So as far as the quantity size, the absolute value size of how these evaluate, those would be the same thing. So the only difference between these two things is going to be that if you're going up into quadrant 1, you're a positive, and if you're going down into quadrant 4, you're going to be a negative answer. So here's how we're going to summarize it. We're going to write that the sine of negative theta, okay, and I'm going to write it in this order because if you get the sine of a negative angle, it'd be nice to be able to change it into a positive angle. Okay, so if we had the sine of negative theta, overall that is the same thing as the sine of theta, except it's going to be the opposite value. So it would be equal to the opposite of the sine of theta. You can almost think of it as being able to factor that negative out to the front. That is not true. That is not exactly what we're doing, but you can kind of imagine it that way, that if you have a negative angle in here, you can just move the negative sign to the outside. All right, so then let's take a look at cosine. Cosine's a little bit different. Okay, remember that for cosine, we are positive on the right and negative on the left. We're positive right, negative left. So if you rotate up theta or rotate down negative theta, you still end up in a positive quadrant. So it really doesn't matter if you're going up or if you're going down. And that's even true if you rotate all the way, into quadrant 2 and all the way into quadrant 3. Those would both be negative quadrants. So the cosine of negative theta is actually the same thing as the cosine of theta. It would be the same thing as the cosine of theta. All right, let's go ahead and verify this before we move forward into the other trig functions. Let's choose an angle measurement. Let's go ahead and go with 40 degrees. I think that would be a good choice here. Pretty much any angle would work, but let's just go with 40. All right, so my claim here for the first one is that if I type in the sine of negative 40, that answer should be exactly the same as the opposite or negative of the sine of 40 degrees. Okay, so we're almost taking that negative and just moving out to the front. And these do evaluate to be the same. Just showing us that if you have a negative angle in there, you can rewrite it with a positive angle and then just make sure you negate the whole thing. Just have a negative in the front. Okay, so for cosine, these should end up being the exact same thing. I can do the cosine of 40, actually cosine of negative 40, get that answer, type in the cosine of positive 40 and see that I get exactly the same answer. Now you can go ahead and do this with obtuse angle measurements or any other type of angle that you can think of and it would still hold true. Let's go ahead and just do a really large number. Cosine of 220 degrees. All right, cosine of 220 gives us that number. Ooh, coincidentally the same thing here. What would that mean? That means that its reference angle is the same, right? 220 is actually 40 away from 180. All right, so let's type in the cosine of negative 220 and see that we get the same answer again. All right, so let's go ahead and start thinking about the other trig functions. The reciprocal to sine is cosecant. And being a reciprocal of each other has nothing to do with positive or negative, has nothing to do with that. So the same rule should apply here for the cosecant. The cosecant of negative theta is going to be equal to the opposite of the cosecant of positive theta. All right, cosine is the reciprocal of secant. So the secant of negative theta should be equal to the secant of theta. These are not opposites of each other. For sine, they'll be opposites. For cosine, they will be the same. All right, and then last, what would we have here? We'd have the tangent of negative theta. Got to figure out what that one would be. We also have the cotangent of negative theta, and think about what that will become. Now, previously, I demonstrated that the tangent is the same thing as the sine divided by the cosine. Okay, the tangent is the same thing as the sine divided by the cosine. The cosine with negative angle measurements doesn't change anything. It doesn't become its opposite. However, the sine does change. So if one part of that fraction does become the opposite, then that means this will become the opposite. Okay, so we can have a negative in the front, just like sine. And cotangent, same thing there. We can move the negative out front. All right, and we get that, and we'll go ahead and verify that one as well. So let's type in the tangent of negative 40. We get that answer, and then I'm going to type in negative tangent of 40 and see that we get the same thing. And of course, for cotangent being the reciprocal, that would also be true. All right, so let's go ahead and take a couple of things that we've looked at here and use them to simplify an expression. All right, so what we have is a fraction with the sine of negative theta over the cosine of theta. Now, one of the things that you might remember that we just talked about here is that the sine over cosine, the sine divided by the cosine is the same thing as tangent. So in a way, I can already start to imagine that I can compress this down into just being a tangent. Unfortunately, you can't do that if the angle measurement inside a sine is not the same thing that we have inside a cosine. So using our negative identities, I can actually take that negative from inside the sine and move it out to the front. I can rewrite this as negative sine theta over cosine theta. I can write it that way. And now that these two look the same, I can change that into a tangent theta. And we still got the negative that we moved out front, so this becomes negative tangent theta. All right, next what I'm going to do is give you a list of the Pythagorean identities. We have 3 of them, 1, 2, 3. The first, which is this, we're actually going to prove it in a moment. The other 2, we're just going to record them down. All right, so our first Pythagorean identity is sine squared theta. What that means is that we're taking the sine of theta and we're squaring it. So it's a weird spot where that 2 ends up. We actually just place it there. But what it means is that we're taking the sine of theta, that first, and then we're going to be squaring it. We just put the 2 there so it doesn't become mistaken for squaring the theta. All right, so the sine squared theta plus cosine squared theta is equal to 1. Okay, now the others that we have, we're going to have 1 plus tangent squared theta is equal to secant squared theta. We also have 1 plus cotangent squared theta is equal to cosecant squared theta. Let's go ahead and prove the first Pythagorean identity, which says sine squared theta plus cosine squared theta is equal to 1. Let's prove that one. All right, to do that, we're going to use our unit circle. Let's go ahead and draw a picture of a circle here. Okay, and I'm going to break up all my quadrants. I already got that picture. Now, any point that would be along this circle here, right? Any point that would be along that circle there actually has some components that goes with it, right? You have a y component and you also have an x component. And we can even talk about the radius. We can talk about the radius. Okay, so I'm going to reference that picture in just a moment. Let's start with what this claims to be true. It claims that sine theta squared. Okay, so sine squared theta means sine theta times sine theta. It claims that that plus cosine squared theta is going to be equal to 1. And what I'm going to do is put a little question mark there for now, because the way I'm going to approach this is just sort of work over here, and if eventually I can show that that's the same thing as 1, then it all checks out. All right, so sine squared theta means sine theta times sine theta. Now remember that the definition of the sine of theta is actually the y value divided by the r. Okay, so I'm going to reference the picture over here. It would be the y value divided by the r. And when we square it, that means we're squaring that whole fraction. All right, so then for cosine, we could take x over r and square that one. And again, question mark, does that equal 1? All right, let's go ahead and do some math. If we square that fraction, we're going to get y squared over r squared. If we square x over r, we're going to get x squared over r squared. And again, we're thinking, does this equal 1? All right, now, because both of these fractions have the same denominator, you can actually just add them together. We can write that as y squared plus x squared over r squared, and then again, does that equal 1? All right, now, if you go take a look at the picture that we had over here, recall that this is actually a right triangle, that would be a right triangle. And with all of these measurements around that right triangle, using Pythagorean Theorem, we know that x squared plus y squared is equal to r squared. All right, take a look at the fraction that we have. We have y squared plus x squared on the top. That's the same thing as this, divided by r squared, which is the same thing as this. So the top and the bottom are the same as each other, which means you end up with one whole. So we can go ahead and erase that question mark. And that identity is true. All right, what is the value of that identity? What it actually says here is that we can take any angle for theta, put it into this, and the answer is going to be 1. Okay, so if I took sine of, let's do 155 degrees. Take the sine of 155 degrees and square it. By the way, when you type it in a calculator, it may look different than this. You can't actually type it that way. This is the notation we use on paper, but this is how it'll look in the calculator. All right, so if we take the sine of 155 and square it, plus the cosine of 155 squared, we get exactly 1. And you can do this with radians, and you can do it with negative angle measurements, you can do it with anything. It will always turn out to be 1. All right, for example number 2, we're going to do another simplifying problem. This one is going to reference the Pythagorean identity that we were just looking at there. What we're going to start with here is some math. We have two binomials that are being multiplied together, so we're going to use some distributive property here. We're going to go ahead and multiply the 1 by each of those terms, which is going to give you 1 minus sine x. That is just distributing the 1 to each of those. So you get 1 minus sine x back. Next, we're going to distribute the sine x to both of those terms. That would give you a positive sine x with these two, and then multiply sine x by negative sine x, we get negative sine squared x, right? The two sine x are multiplying, but we have a positive and we have a negative, so we end up with a negative. These two terms are going to cancel with each other. They become a 0. So that leaves us with 1 minus sine squared x. All right, and that may seem like we've simplified it because we did the math and it's become that. But recall the Pythagorean identity we were just looking at. It said the sine squared theta, but we're going to do sine squared x here. Sine squared x plus cosine squared x is equal to 1. And you're going to notice that this piece and that piece, they are both here. Okay, but how does it relate? Well, if you were just to take the sine squared x and move it to the other side by subtracting it, if you were to subtract it to the other side, remove it from here, we get that expression. We get it over here. So that means we can continue to simplify this a little bit further down to cosine squared x.
Wait, what?